a sometimes more, sometimes less occasional Scala compiler hacker. I've done a fair bit of work on the Scala compiler recently. I'm also one of the co-founders of sort of an umbrella group of Scala libraries which focus very much on functional programming and trying to get the most out of the various interesting and intricate parts of Scala's type system. One of those things which we'll talk about a little bit in this talk is my generic programming library, shapeless, which will be appearing as an example for the new language feature that I'm proposing here. Before I start, I just wanted to get a quick sense in the room of who here is comfortable with sort of typed functional programming languages like Scala, like Haskell, like similar. Quick show of hands. Okay, that's everybody. That's brilliant, marvelous. Is everybody here comfortable with the concept of type classes? Show of hands of that as well. Okay, that is also everybody. That's very, very helpful. If there's anybody here who isn't a functional programmer, doesn't use this kind of idiom, I was trying to come up with a very quick analogy for sort of OO people. And a type class is kind of like the adapter pattern made automatic or something along those lines. But anyway, right. Okay. So, if we're going to add kind-polymorphism to Scala, I guess it helps to know what it is first. So it's a form of parametric polymorphism. I think we're all familiar with basic parametric polymorphism as you find it in most modern typed languages. Basically, given a type, you typically have a hole in the type which can be substituted for by some other type. So, for example, a list type will typically be parameterizable by the type of its elements. So we can have a list of T can be instantiated at a list of int, list of string, list of Boolean, and our compiler is going to ensure that basically our uses of a list with suitably parameterized are consistent with the type of its elements. So it will ensure that we can only add integers to a list of integers, and it will ensure that the elements we retrieve from a list of integers are all integers, and so forth. And one of the things we say about type parameters of this sort, so this is, if you like, a simple type parameter. It has it can be instantiated by any complete type. So, for example, int, string, boolean, they're all complete types. They themselves have no holes in them. In languages like Scala or like Haskell or some other languages, we also have higher-kinded types. So we can parameterize types by types which themselves have holes in. So here's an example of a functor. This would be, say, the type defining a functor type class. It's parameterized by a type which itself has a hole. So functor, you could very crudely summarize as being the kind of types which support some sort of map operation. So, for example, mapping over a list, one might. So, for example, if one had a list of strings, one might map a length function across a list of strings to get a list of integers. So the map is going to retain the shape of the type whilst substituting the elements in it. So we can define functors for things like list, for things like option, for things like vector. The key thing here is that the type parameter of the functor type class itself has a hole in it. And we call these kinds of types types of kind star, arrow, star. So kind polymorphism is a form of parametric polymorphism where we kind of want to be able to actually fill in the hole in a type with types of different kinds. Okay, so you might wonder, well, where is that going to be useful? This is actually, I think, one of the key topics of this talk, is that actually finding out what useful examples of this thing is actually one of the interesting things to do. The places where you tend to see this coming up, certainly in Scala, we have various things in Scala has a macro API which works with Scala types. It has a reflective API, a runtime reflection API, which again works with representations of types. There is a type of reified types called a type tag in Scala, which we would actually really quite like to be kind-polymorphic. We'd like to be able to sort of find sort of the type representation of, say, all of an int, list, which is a type with a hole in it, map, which is a type with 2 holes in it. So the question there is, what might we put in the place in the type tag trait that would allow us to do that? Haskelers can do things like this. They have this thing called a polykines extension, which allows them to do that. So this typable type class in Haskell it has some things in common with the Scala type tag. It differs in some ways, and the key thing here is that you can see that we've defined instances, or at least the compiler provides instances for types, a type like int, and also a type like list. Int is a type of kind star, no holes. List is a type of kind star arrow star, 1 hole. But we can provide instances of the type class for both of those types. Okay, so why? Why do you want it? So the main reason is boilerplate elimination, and I think this is fairly clear in the Haskell typable example. You can define with polykines. You can define typable in this way. Without polykines, you need something like this. Basically, you need to replicate the definition of the typable type class for each of the different kinds that you want to support. So here we would have typable for types of kind star, typable 1 for types of kind star, arrow star, and then you just keep going until you get bored. 1, 2, 3, 4, 5, and then you would provide instances of the different types. This is kind of annoying. In the Scala case, you can see here what you actually end up doing, because we in standard Scala we don't have kind-polymorphism. What you end up doing with things of this sort is that you end up sort of artificially plugging the holes in some way or another. So, for example, to get hold of the reified type of list, you start by just stuffing something in the hole, any, for example. That gives you a fully applied type, so you get list of any. That's not the same type as the list type. So you then need to perform an operation on it, extract the type constructor, effectively poking the hole out to get the unapplied type that you actually wanted in the first place. There's a sort of idiom that, this is actually a very common bug in Scala macros and uses of reflection, to sort of use the Scala underscore meaning don't care, meaning something in that position. That actually gives you another different type, because that's actually syntax for an existential type, which is actually quite different from the type list. What we really want to be able to do, I think, is to write something like type of list and have that work in the same way as type of int or string. My library shapeless has a typable, which is quite similar to Haskell's typable, and it also has the same issue. It would be nice if we could write instances for the typable type class and use them in a kind-polymorphic kind of way, in the same way that the Haskell version can. Okay. So why? Is that enough? Is that really compelling? Sort of kind-polymorphism is sort of fancy highfalutin term. People, just to let people down quickly, there's not going to be much in the way of, there's not going to be really any theory about this stuff. This is more of a conversation about sort of programming language, sort of pragmatics, I think, rather than anything else, and ergonomics. So you might be concerned that kind-polymorphism sort of opens up all kinds of potential interesting, nasty holes and complexities in our type system. Is Girard's paradox lurking in the background somewhere? Should we be worried about that? Is it really worth introducing this fancy type system feature just for these kinds of examples that I've shown you on the previous slide. You know, and is the boilerplate really that terribly bad? Particularly if it's something like a typable class where you know, the compiler standard library implementer is going to be providing those instances for you anyway. Well, I think it's probably, for the example we've seen so far, it's really not that compelling yet, and the boilerplate isn't so terrible. So let's try another example. So generic programming is it was kind of introduced. There's an annex to ICFP, the main functional programming conference, called used to be called the Workshop on Generic Programming. And a few years ago, the person, I forget who it was now, who was kind of introducing the first session, sort of described, was trying to come up with a deft summary of what generic programming was, and came up with the sort of the sentence along the lines of generic programming is kinds of polymorphism that your programming language doesn't support yet. Basically, generic programming in general and shapeless in particular, it's a sort of toolkit. It's a toolkit for allowing you to work with and manipulate algebraic data types in a very general way. Basically to manipulate them in ways which sort of cut with the grain of their structure as sort of sums of products of their constituent elements. It works in terms of a compile time generic representation, and it doesn't make any use of runtime reflection. Most of the work that shapeless does is done via, if you like, normal, although somewhat advanced Scala code. It relies on things like defining sort of type level induction using implicits. I'm not going to discuss that in any depth in this talk. It also uses path-dependent types and singleton types for various things. But it does depend on a few Scala macros to do some of its work. And in particular, one of the things it does is it relies on a Scala macro called generic, which basically does the hop between the representation of an ADT in its normal Scala form and the generic representation that we work with. Generic is a type class that looks pretty much like this. It's indexed by a type G, which is the algebraic data type, and it will take you onto a representation type. The representation type will be, in the case of if G is a product type, like a Scala case class, it will take you onto a representation type, which is a product, something which is essentially nested pairs. If it's a sum type, it would take you onto something which is like nested ithers, for example, which will give you a choice between the different possible branches of the algebraic data type you might go down. Then it provides a pair of functions, one to take you from your ADT, your algebraic data type, to the representation type, and one to take you back. And then the essential idea of working with shapeless is that you would then make use of shapeless's toolkit for dealing with the generic representation to do interesting kind of things with the type. So, for example, we might have, suppose we have, say 3 product types, an A, which contains an int and a string, a B, which contains a Boolean, and we're trying to glom together 2 instances of these products together to make a C, which has got 1 field for each of those elements. The way you can do this using shapeless's toolkit is you can basically write a concat method which requires instances of generic for each of the ADTs, and then it will map the 2 source ADTs into the generic representation using a general product concatenation operator to glom them together, and then it maps them back into the representation. Into the C ADT. This is fully statically type checked. There's no runtime reflection involved. All the types that are involved here are traced all the way through, and it kind of does what you would expect a sort of I've had various people kind of describing this, sort of saying that the impression they got from this kind of code was that it almost looks like, you know, how you would write code in a dynamic language, even though things are actually fully statically checked. There are lots of similarities between a similar language feature in Haskell. It's the generics feature, which was initially put together by Andres Lowe, and I forget who the second author is, but anyway, it's one of GHC's many extensions, and it provided a great deal of inspiration, and it works in a fairly similar-ish kind of way. Okay, so initially, shapeless only had generic representations for types of kind star, so fully applied types. So that would be, for example, a type like option of int. So option, although it's a type of kind star arrow star, once it's applied to an integer, it's a fully applied type, so that resulting type is of kind star. And you can kind of see from the definition of the trait that it's got to be the case. In Scala, at least, you indicate the kind of a type parameter by the syntactic form of the type variable. So a type G of that sort, without any little square brackets after it, is always going to be a type of kind star. And ditto, the representation type itself is also a kind star. So it's a fully applied type. So we will take an option of int onto, in this case, because that's a sum type, it would be an either of what would it be? An either of a product type or nothing. But again, it's something which is fully saturated. There are no holes in that representation type. It covers an awful lot of ground. It's pretty much what you need for many of the actual practical uses of shapeless as a generic programming library. Lots of which are basically involved with doing very general sort of serialization libraries, turning families of turning ADTs into, say, JSON, for example, and back again. I mean, there is a small cottage industry of people writing libraries on top of shapeless, which do this kind of stuff. It is actually, I am quite surprised how widely it's used. I did a quick in the general Scala ecosystem. I did a quick check on my Maven Central download stats recently. It gets about 300,000 downloads a month, which is quite a lot. I mean, it's not you know, compared to the sort of the general JVM ecosystem, it's not that big, but it's a significant amount. So it's used widely. Various people have anecdotally said that almost every Scala program somewhere or other indirectly has a shapeless dependency somewhere. That's an exaggeration, but anyway, it's used a lot. So generic programming of this form covers a huge amount of ground. It's incredibly useful, very, very practical. It's a language feature that we definitely want. Okay, however, that's not quite enough. We kind of want to be able to have generic representations of other kinds as well. So it'd be nice to have at least representations for things like list or option. So option, but in this case, without the hole being plugged. I believe GHC has a generic one, which does something along those lines. Shapeless also has a generic one. And here you can see, again, from the syntactic form of the type argument for the ADT and also the representation type, that we've switched to, now we have a different kind. Here our ADT is of kind star arrow star, as is the representation type, and the to and from methods that take us into and out of the generic representation now become polymorphic as well. So we can do lots of interesting things with this. So, for example, whereas with the plain generic, we can do interesting, useful things like define encoders and decoders. With things like generic one, we can define automatically define type class instances for things like functor, foldable, traverse, and those kinds of things, which are very, very interesting. They're maybe less directly applicable than things like codecs, but they are enormously important. They're very, very useful. in lots of contexts. Okay, I'm going to skip over the demo of this. I hope that's clear enough. So the real problem is that, let me just see where we got to. We end up with a proliferation of generic X type classes for, I've shown you two kinds, but you know, kinds don't stop at star, arrow, star. There are lots of interesting kinds which go well beyond that. Where do you come up with a principled stopping place in this proliferation of alternatively kinded type class instances? And it's very hard to know exactly where you would stop. And although it's kind of not so much of a problem if you're writing a library, if what you want to do is perhaps incorporate a feature like generic as a language primitive, which I think in many ways is really exactly where it belongs, I think you need to have some kind of principled way of working out what the limits are, what the range of possibilities are, and ideally you want to be able to remove arbitrary restrictions as far as you possibly can. One of the rationales for wanting to see generic make its way into the language proper is that, as I mentioned, I mean, the generic itself is a macro primitive in the shapeless library. In Scala 3, otherwise known as Dotty, the entire macro infrastructure is likely to change in fairly radical ways. It may very well be the case that the replacement for macros in Scala 3 will probably not support the kinds of quite possibly not support the kinds of macro features which generic depends on. So it'd be nice to have some kind of route out of that. And I think working with the idea of baking it into the language as a primitive, I think is definitely an interesting idea, and I think it's something to be pursued. But the problem we've got is that you know, generic 1, it feels very ad hoc. It would be nice to have some alternative mechanism for dealing with it. I just want to give one motivating example of another kind. So this is something which maybe gives a hint of why we actually have kind of a problem with kinds. This is something called a higher order functor. It's kind of, I think the Haskell version of this that you see people playing around with is called H functor. Basically, it's the kind of thing that will take, if you see the definition of an order type here, so it's an order parameterized by an f. It has an item in that f, and it has a quantity in that f. We want to be able to apply a natural transformation to this kind of thing. And the idea here, for example, might be to represent optionality in a type. So, for example, we might want to index order by option, and this could represent sort of a partial value of an order type. So we might have, so option of string, option of int for the item and the quality and the quantity. It's a very typical thing in, say form-filling applications to want to be able to represent partial results where things have been sort of partially done, and then you skip forward, skip back, undo, redo, this kind of thing. But at some point, you want to be able to produce a complete item, at which point you would want to be able to produce order parameterized by ID, where ID is a type constructor which is essentially transparent. So in other words, it will give you a guaranteed string for the item and an int for the quantity. The operation that you might use to perform that will be a natural transformation, which takes you from option to ID. Well, not option, an option with a default, which takes you from an option with a default to ID to kind of fill this out and complete it. Again, with a suitable generic, it's possible to derive a type class instance of this sort and have that produced automatically for you by the compiler. But if you notice the kind here is completely different. Here we have a type which has a type parameter, which itself takes a type parameter. So so here our first type parameter itself has a type parameter. So this is something which doesn't fit into either the generic or the generic 1 model. And we end up having a really, really horrendous proliferation of kinds which really there is no interesting way of corralling these into a simple sort of enumeration of kinds in a way that I think would support a sort of a clean and tidy language feature. Okay, so can we abstract away the differences between the different kinds here? And this is something that you could experiment with. It's something that I've had a look at. So your initial problem when trying to solve this problem is that there is literally nowhere in a Scala program where you can put types of different kinds. This is a syntactic, a semantic restriction. So, for example, we cannot have a type generic which can both take a fully applied type list of int as its type argument and also list. Equally, if we go for the generic 1 style with the parameterized types, it cannot take both a list of int and a list. So there's nothing apparently we can do here. However, what we can try to do is define some auxiliary traits which are going to try and abstract away the differences between the kinds. So here we might attempt to wrap a fully applied type in a type which captures the idea that this is a type of kind star, and then we could repeat this for capturing a kind of star, and then we might hope to kind of just fill these in as much as in a relatively ad hoc kind of way and sort of do that. Having done that, we would need to then represent the application of such a type to a value via something that can capture the fact that we've embedded these represented kinds. So we define a GADT which is going to capture the idea that types of kind star are applied to nothing and types of kind star are applied to some type T. And then we can try and work with that. And you end up with a generic which looks a bit like this, where you make use of the apply type constructor here, and you end up working with this representation embedded in a sort of lifting.
What's the kind of G?
The kind of G there is star. So it's So we're wrapping either a list of int in a K0. So K0, all of the Ks here. If we go back, once they're fully applied. So in both of these cases, the first type argument to generic is going to be a type of kind star. So K1 of list is of kind star. K0 of list of int is also of kind star. Does that make sense? You look worried.
Keep going.
Okay. Right, I'm actually not going to do the demo because I'm not going to have time. Is this making sense? I mean, hopefully I'm getting. So, key thing here is, hopefully this looks pretty horrible. Actually, this looks like something you don't want to do. It's not very nice. So this is how you might attempt to model kind polymorphism in existing Scala. Okay. So I won't demo it. It kind of works. It's pretty clunky. Okay. So a little while ago, I and Pascal Voitot, who's another Scala person who likes doing crazy things with fancy types, we decided to just take a quick pass at seeing if we could just stick kind-polymorphism into Scala somehow or other. We reckoned that actually in terms of the internals of the Scala compiler, there was enough riddle room that we will be able to actually internally represent kind-polymorphism. And the main thing to do was to actually just try and get over this hurdle, this syntactic hurdle, of there being nowhere in a Scala program you could syntactically put types of different kinds. So that was essentially what we thought we would do. So we'd support type parameters which can take arguments of any kind. We then use type-level computation to do all the rest of the work. So Scala makes use of implicits to essentially compute over types. It would take far too much time to explain how this is done, but essentially you can use implicits to essentially do pattern matching and structural recursion over types at compile time in a fairly general kind of way. That's kind of the core essential idea of how shapeless works. So we're kind of thinking, okay, if we can just produce type variables, type arguments which can take types of any kind, we can then do type level computation to do all the other kind of things that you expect to be able to do with polykinded types, and maybe make that work. So we deliberately avoided trying to do anything relating to polykinded type applications. So that apply GADT, that's not going away. So that was a collaboration between the two of us. We did a prototype of it. It's included in the type level fork of the Scala compiler, so you could play around with it if you wanted to. And the end result is something like this. So we end up with bounds of any kind, which indicate that we can actually fill the hole in generic with types of any kind. You'll notice, as I said, that the apply type constructors are still there. Okay, so as I say, polykinded type application is still present. Again, I'm going to skip the demo. It's not going to add very much here. It's a little bit better. It's still pretty clunky. And we thought it was an interesting experiment, but actually, that's as far as we're going to go. We're never going to persuade anybody in the mainstream Scala community to actually incorporate this as a language feature. We have other things to do. Let's get on with something else. So we decided to park it and maybe revisit it. It didn't really feel like it was getting rid of enough pain to make it worth the effort of pursuing at that point. Okay, plot twist. It was adopted in Dotty, which is the sort of code name for what will hopefully relatively soon become Scala 3. So the initial implementation was quite similar to the prototype we had in the type-level Scala compiler. It actually turns out that so Martin Odersky realized there were actually some quite interesting uses for the form of kind-polymorphism actually in the internals of the Scala compiler, and also it actually fits in quite nicely with some aspects of the theory, which I'm not going to touch on. And it seemed, evidently a relatively simple thing to add. And so it's actually present in the current releases of the Dotty compiler in more or less the form that I've shown you. So the interesting thing is it doesn't actually take us any further than that last demonstration. There's still no polykinded application. However, it kind of revived our interest in pursuing the idea. And so we thought it would be interesting to see where you could go further beyond that. So as I said, sort of the second hurdle, once you've actually found a place in a Scala program to put types of different kinds, is how do you deal with polykinded applications? So let's have a look at what this kind of looks like. So this is the generic from the previous example. So the type we're representing, the G, is of type any kind. The representation of type is of any kind. We're relying on this apply type constructor to handle the application aspect of it. Then when you're providing instances of this type class for box here is just just a placeholder type. It's just a simple product type which contains an element of some type. So you can see that to conform to the interface that the generic trait is presenting, we need to express the projection methods in terms of the apply method. However, once we know what the concrete type we're dealing with is, we can delegate the implementations of those to methods which are expressed in terms of actual applications of the type constructor that we're interested in this case, box, and the actual representation type that we're interested in. So we can do that very simply, and it kind of seems like the first two lines there, expressed in terms of the apply type constructor, they're pretty much mechanical. They're certainly the kinds of things which we expect that a compiler which knows about the structure of the box type ought to be able to generate automatically for us. So suppose we could actually just throw all that stuff away, at least in terms of the code that people write. And suppose we can impose some additional constraints on type variables so that we can say that we want that when the compiler is type checking, unifying types, that it's going to enforce various kinds of constraints on kinds. So we can say that, well, one thing we do know is that we want the representation type to have the same kind as the type we're representing, because the holes in the ADT should line up with the holes in the type of the representation. And then we have to have, so we're going to capture that by having this sort of kind of operator here, rather than saying that representation is an arbitrary any kind. G can be any kind. Representation is, well, it's got to be whatever kind it is. It should be the same as the kind of a representation. Then we're going to have something here which allows us to say that it's a sort of an invisible constraint in the way I've written it. This is hypothetical syntax. It's not. Perhaps there should be something explicit here on the bound of the method level type parameter here. But basically, the constraint is that whatever the kind of the ADT and the representation type is, I should correspond to some set of type variables which are of the appropriate number and corresponding kinds to be plugged in here. And we can just rely on the compiler to work this out for us. I mean, this should be an entirely mechanical process. Then we would have in our an instance of generic for this type. Well, the code that we want to write, or at least the code that we want to interact with, bearing in mind that all of this stuff is going to be generated by the compiler anyway. However, the to and from methods are the types that an end user, consumer of this type class instance is going to be wanting to interact with. These are the ones that we want people to have to invoke. We don't want them to have to explicitly deal with an explicit type application, boxing, and wrapper around their type. So this is what we want to write. And what we want is for the compiler to generate essentially the code that I showed you on the previous slide, where we're doing the delegation from the wrapped kind of lifted type application into the unlifted one, and have that done for us. And I think this looks a lot better. I actually think this is interesting enough now, and it's sort of clean and tidy enough now that you might actually say, okay, that means that something like a generic type class of that sort is simple and compact enough that it could form a language feature that you could consider writing a specification for, and trying to encourage the Scala community to adopt and work with. And I think something along those lines is actually potentially quite interesting. So I'm going to be pursuing this. Sort of next steps is to put together a prototype of the polykinded application stuff and get that going in a type-level Scala compiler. Also do the same in the extend the Dotty implementation in the same direction. Play around with it. So one of the things that was interesting, I mean, if you actually Google for uses of kind-polymorphism, you'll find very, very few hits. The main ones are going to be things like typable. And one of the reasons is because it's actually quite fiddly to deal with, and sort of language level support for it is not wonderful. I strongly suspect that once it's available as a language level feature that people can play around with in a relatively unencumbered kind of way, people are going to come up with lots and lots of examples. I think the higher order functor example is actually surprisingly compelling in a way. I mean, I think the kind of problem that is addressed in this tiny little toy example of taking sort of an ADT with optional bits into an ADT with no optional bits left in it is actually, excuse me, is actually a problem that people have all the time. And being able to do something interesting with that in a relatively simple and straightforward way is actually really quite a compelling language feature. But I suspect that once this stuff is available for people to play with, lots more equally simple and small and hopefully compelling examples will come out of the woodwork. Okay, I'm done. Questions? I'm sure there will be some. Yes. Sorry, I think there's a microphone coming for you.
Hello? Okay.
Yes.
If you had some way, for example, of interacting with a higher level of type, for example, a type of types,
yes,
would it solve your problem entirely? Because you could say this thing has the type of types, and therefore you could put any kind of types inside it that is type to type to type.
I think the answer is yes. I mean, okay. if we go to full dependent types,
yeah, then
the whole picture has changed. I don't think Haskell and Scala are both inching their way in the direction of dependent types. Whether they actually get there in the end is a very open question. I think drawing inspiration from the kinds of things that you could do in languages like Idris or Agda is very, very useful. I think it's very helpful to try ideas out in those languages and see to what extent you can bring stuff back. I think Simon?
I'm Simon Peyton-Jones. Thanks for your talk. So I've got two questions. One is, with these higher kinds, like the one you just showed with star, arrow, star, arrow, star, I always wonder how you're going to deal with variance, both covariance versus contrary. So that's just a thing, okay, a sort of complication in Scala, yes, that you kind of got to bite the bullet somewhere for there. So yes, that's number one. The second is, so this is a little piece of experience for Haskell. In Haskell, we have for a function, you can supply a separate type signature that says this is the type of this function. Say f : type, and then you give its declaration. In Haskell at the moment for data types, you say data type, A, and then we sort of infer its kind, right? And we finally bitten the bullet and say, no, we're going to let you specify a separate kind signature for type constructors because it's just much more straightforward to do so, much more explicit. And the same thing was happening in your slides when you were saying, oh, you got underscore, open square brackets, underscore, close, and you were saying, that really means star, arrow, star, arrow, star. Yeah, and particularly when you get to kind polymorphism, then you end up with these kind of things. Why not just say, for all k, k arrow star to k to star? That would just be much more direct. And I'm wondering whether you'd even considered, I know that's a syntactic move, right? But from our experience, it's going to be something you'll be forced into sooner or later, and you might as well make it sooner. Right. We're dragging, kicking, and screaming. That's where we've gone.
Yeah, sure. I'll answer the second question first because I actually lost the first question while I was listening to the second one. So I'll ask you to remind me of that. So actually, there's something very interesting going on in Dotty. One of the things that in Scala we can take advantage of is, believe it or not, subtyping. So you can express the idea of a kind as a subtype relation from some other type. So for example, you could express, I forget exactly how this, so this is actually something that Martin's working on in Dotty. So effectively, you kind of erase the type parameters and you rely on an injection from your types into something where all the holes have been plugged. You nominate some sort of base level types which are going to function as kinds. So having done that, you then have if you like, a type that you can work with as effectively doing as a surrogate for your kind. Then actually the idea of representing kind constraints via the subtype operator actually makes huge amounts of sense. So kind of G is actually going to be some concrete type. I forget exactly how it works out in Dotty, but hopefully that makes some sort of sense. And this also relates to, actually, I now remember your first question was about variance. Variance just generates more kinds in Scala. So this is another reason why I mean, it's actually a nastier problem for Scala than it is for Haskell, because as well as generating kinds just in terms of arities, or the kinds of elements, we actually generate kinds for every time you see a subtype bound on a type variable. That gets you a new kind. So being able to abstract over variance is actually a form of kind polymorphism. So we actually get an extra win in Scala from being able to do this kind of thing. So we would just capture variance in kinds and kinds via subtyping, which is obviously not an option which is available to Haskell. It's maybe not a great option, but it's certainly something which is available almost for free in Scala, given the structure of its type system.
Okay, thank you very much.